In the previous video, we have used test time augmentation to boost our model performance. But what if you could take it one step further? In this video, I'll show you how to improve traditional TTA using a learnable and smarter approach. So first of all, let's understand what is test time augmentation. It is a technique to improve a model performance during inference by using augmented version of test data. How it works? We apply different augmentation techniques such as flipping, rotation to the test image. Then we predict on each of these augmented version of the test image. And at last we average all those predictions to get the final output. Now we'll understand the limitation of traditional TTA. So first problem is it is non-learnable fusion. Final prediction is simply average. We don't consider like one prediction could be really bad, one could be really good. So we scale them accordingly, we weight them accordingly. Second, the main disadvantage of this traditional TTA is that all augmented versions are weighted equally, even noisy. Even if you can weight them manually, that would also be worse because now you don't have the control. And that's where comes the learnable test time augmentation. So it's a method that learns how to combine prediction from multiple augmented input using a data driven trainable strategy. So here in both the cases, that is traditional TTA and the learnable TTA, we're going to use same augmentation technique but learn how to weight select among them. Here it learned to combine feature of predictions using a simple neural network. And that neural network is trained on a small validation set, so no extra labels are required. Now let's do some performance comparison. So here's a table. You can see we have three methods. First is the normal inference, second is traditional TTA where we weight all the prediction equally, and last is our learnable TTA where we learn the weight for each of these predictions. So in the first technique, in the normal inference, we can see we have 0.44 F1 and 0.36 as the mean IU. In the traditional TTA, we can see that we got an improvement of 7.9% in F1 and 10.792 in case of mean IU. Now if we look at the third method, that is learnable TTA, the performance even got better. In comparison to traditional TTA, we got 15% improvement in the F1 and a 16% improvement in the mean IU. So that is how effective this learnable TTA is when you compare it with the traditional TTA, because here we learn how to combine those predictions, and even you can extend it further that which augmentation technique is best for which data set and which is not. So it's going to learn that also automatically. Now let's move on to the implementation part of this video. So here we are in our code. So first of all, we are going to import all the libraries which we need for this task. So here are all the libraries which we need, and we are going to use PyTorch for the implementation of this learnable TTA. Next, what I'm going to do, I'm going to write all the classes and functions and explain them. And after explaining all those, we're going to work on the execution from that main statement. So first of all, we're going to configure the CUDA device or the GPU at the starting only, because that is important. And for now, I'm using a 1050 Ti because my 3090 stops working and I think it's dead. So only God knows when I'm going to get the next bigger GPU. But for now, 1050 Ti is also work. So it's not that you need a bigger GPU for this learnable TTA. Even a smaller GPU is more than enough. Okay, so we have done with our this GPU. Now we have a class called image processor, and what this class is, it handles resizing, normalization, mask processing, and it also has a function which convert mask between RGB and class index format. So it does all that. So I'm going to simply paste it and explain it. So this is our image processor class. So it take your size, the image size, and the color map, that is those RGB codes specific for each class, and from that we calculate the number of class. And here we have a function called process image. So is take the image path, it read the image as RGB, then it resize it, then it transpose and make this image to channel first, because by default when you read an image using any library, it read it as height, width, the number of channel. But PyTorch take channel first approach. So now it is channel height and width. Then we normalize this image pixels by dividing them with 255, that is the maximum pixel value. So it convert all the pixels in the range of 0 and 1. Then we convert it into a PyTorch tensor and we give it to our device. So by according to everything, it should use CUDA, but if there's any error, it's going to move to the CPU. Next we have this mask processing, where it take the mask path, read it as RGB, because now we are working with multi-class image segmentation. So it should read the mask as RGB instead of grayscale, because now it contains more than one class and those classes are represented using RGB code. Then it resize the mask, and here we convert this mask to a class index mask. Okay, because for the training we usually need this thing, because your unit model which we have already trained, so during training it won't take your RGB mask, it's going to take a normalized mask which contain value from 0 till your class, how many classes you have, like 0 for background, 1 for V1, 2 for V2. So like this, it's going to be a single channel mask with height and width specific, same as the image, and all it contains is a value for all the classes, like what each pixel belong, like each pixel belong to a specific class, it should be specified with that. So that is how your model trained. Next we have a function called mask to RGB. So it convert this index mask which contain all the classes ranging from 0 till number of class to RGB mask. Now we are done with this image processor. Now we have a function called apply augmentation. Let me copy the code for this, and if you have already watched my previous video on the test time augmentation, you already know this function. So this function basically apply test time augmentation. It contain original image, then we apply this horizontal flipping. Okay, sorry, yeah, now it's correct. Oh, sorry, it should be like this. Yeah, I'm sorry. So where we are, so first of all it applies original image, then we have horizontal flipping, then we have vertical flip, and finally we have horizontal plus vertical flip. And I've used these three augmentation in the original image in the normal TTA also. If I show you the code, you can see original, horizontal flip, vertical flip, horizontal plus vertical. So for better comparison, I've used the same augmentation in the same way. Okay, so that it's fair to compare both these techniques so that we know how much improvement we got. So it is fair. So we are done with our apply augmentation. So what does it give back? It give back the predictions. It give back all the prediction, because in this function we just append them. We don't calculate a mean of them and do next thing. Now our next class is Learnable TTA. So you can simply say it's a neural network which learns weight. So it's a small neural network that learn to combine multiple predictions. Instead of simply averaging, it's assign learnable weight to each augmented version. So here we have number of transforms. So we can say 4. 1 is the original and rest 3 are the. Then we have this weight, because now we need to calculate weight for each of the predictions. So number of transform basically means number of prediction, because transform are 3, but 1 is also the original image prediction. So we have 4 prediction. Now we need to calculate the weight. So what we do, we have a PyTorch parameter which is equal to number of transform or number of prediction we have. Then we, in the forward function, we have these prediction, that is the list. So what do? We apply the softmax to get the normalized weight for fusion. Then here you can see the weighted sum of prediction. Here we apply the weight to these prediction. Here you can see the stack and these predictions. So we multiply them and we get the weighted sum of prediction and we give it back. Now comes another function, that is train learnable TTA, because here we also going to train these learnable TTA. So this is small function. So what do? In this function we take a model which is already pre-trained. Then we have TTA module, val x, val y, processor. Processor refers to this image processor which have all these functionalities, and we're going to run it for 5 epoch. So what do? We say model.eval. Basically we say don't train the model, just put it in evaluation phase. Now we want to train this TTA module, so we specifically say train this. Then we have Adam optimizer with the learning rate of 1e minus 2. Then we have cross entropy as the loss function. Then here we preprocess all the validation data, val data, then image. Here we use the image processor to process image and process mask, and then you append all the data inside this. Then one more loop, here we say run it for 5 epoch, because by default we say we want to train this TTA just for 5 epoch. You don't need to do it more than that. Then total loss is 0. Then we have image and target from the val data which we have processed above. Here inside this, first of all we take the model and the image and we apply predictions. So we get a list of predictions here. Then we give it to the TTA module, here this TTA. So it gives you the weighted prediction, the final prediction. So this final prediction now need to be learned. So now here we learn it, because here we use our cross entropy as a loss function to calculate the loss. What is the difference between these two? Simply we can say. So here we try to optimize these weights so that our prediction is nearer to the target. So here we learn all this thing and we print the loss. So this is our learnable the function which trains your this learnable TTA. So now we have those, this learnable TTA would have those weights which we really need. Now comes the last function, which is evaluate. That is the main function and the bigger function. So let's go to the starting of this. So first of all we have in this function evaluate. It take your pre-trained unit model, then TTA module, save path where we're going to save our predictions, then test x, test y, the test images and mask, then your image processor for processing the image. Then we have classes. So here we have two empty lists, time taken to calculate the FPS. Then we have score. So we create two folders inside our save path, that is mask and then joint. Mask will contain individual predicted mask and joint will contain the joint. It would contain image, ground truth and the prediction. So here prediction would be the combined weighted sum of all the prediction. So here we iterate over the tested data, that is images and mask. First of all we get the name of the image, because we also need to save the images in these respective folder. So name should be exactly same. Then we process image and mask. Now here we save the image and mask for visualization. Then we come with torch.noGrade because we don't want any gradients to be calculated here. Inside it we say, so we start the time, we apply different augmentations to the using the model in the image. Then we get the list of predictions. Then we give it to the TTA module. So this TTA module, again remember, it is going to have this optimized weight which we're gonna pass through the softmax. Then we have the weighted sum of prediction. So now we have trained it, so it would have nice weights, so it would give you a much better prediction as compared to the normal or traditional TTA. Then here we calculate the mask using the argmax. Then we append how much time it has taken for these steps. Now here using these lines we save the images. Okay, so we save a concatenated image which contain original image separated by a line, white line, original mask separated by a line, and then a prediction. So this again, let me tell you, this prediction is weighted sum of all the predictions. Then we save both of them, a joint representation, a joint image, and a single mask. Then here we calculate the scores, that is the evaluation matrix, that is F1 and mean IO, and same we do, we append them basically here, and calculation is done after that here. And here we calculate the mean FPS, and we also save this. I think we can do it like this. Yeah, we don't need this. Okay, so it's done. Now comes the execution part. So we do it. I'll again simply paste it. So first of all, we seed the environment, and we are using the same seed number every time, that is 42. In most of my experiment I use the same seed number. Then we have a configuration for which contain, it's a dictionary which contain all the values which we need. First of all, image size. So we have used 256 by 256 to train our unit architecture on the weed segmentation dataset. So is the path to the dataset. Let me show you images and mask. I think I should have shown you at the starting. So these are images of size 512 by 512 and their respective mask. So it contains two main class and a background. One class is in red, one is in background. So this is how it works. You can see this is the data set. So this is a simpler, really simple data set. That's why I've chosen this. Now here's the RGB code. First for background, then I think it's one for red and one for green. Yeah. Then we have classes, what they represent: background, weed1 and weed2. Then checkpoint file, the weight file, the checkpoint file for the unit, and this is a save path. This is where we're going to save our result for the visualization, and we want to train it for 5 epoch only. Here we initialize our component. First of all, we initialize the image processor. Then we load our model into the device, that is CUDA or CPU. Then we load the weight file. Now we load the data set. And here you can see we are only using 100 images for validation. That is a subset of TTA used for training. Maybe you can use the complete data set for better performance. But for now, let's use 100 because even my GPU is now 1050 Ti Note 1390. So 100 would be much better. Then we create that create and train the learnable module. Here we have our learnable TTA. We also put it in the CUDA and call our train learnable TTA. And finally, we call our evaluate function. So now I'll explain everything. Let me run this. It's Learnable TTA. I think it's going to take some time. So first of all, for 5 epoch, it's gonna train. So what I'll do, I'll pause the video and I'll come after every process is done. So here all the processes, iterations and loops are done. So you can see 5 epoch, and here's the loss 0.59141333. So this is how the loss is. Maybe you can increase the data size and maybe train it more. You can additionally also save that, but I think I don't need it because it's not taking that much time, even less than 1 minute, just 38 seconds for each iteration, and that on this low GPU. Maybe you can further optimize this code. It's up to you. I don't have any problem with that. But the main thing is that our performances really improve. So you can see 0.67 and 0.63. And now we can also see the result. Okay, I need to, so you can see. So these are our predictions. Now you can compare them with a normal TTA also. All you just need to do is train your model and run all these. That's all. Okay. So that's how you take the test time augmentation to the next level by making it learnable. If you found this helpful, don't forget to like, share and subscribe for more deep learning tutorials. See you in the next one.